Swayam Prabha. Digital India. Educated India.
Today we are going to discuss the modal analysis of beams. So, in the previous lectures we have been discussing about beam models, mathematical model of models of beams, and so today we are going to discuss the modal analysis, which means that determining the eigen frequencies and the modes of vibrations of beams. So, we will begin with a simple case of a uniform Euler-Bernoulli beam. So, as you know that the uniform Euler-Bernoulli beam is governed by a differential equation like this, and along with this we can have we will have boundary conditions. Now, as we have discussed in our previous class, there will be in all 4 boundary conditions. So, suppose if we consider a simply supported Euler-Bernoulli beam, then the boundary conditions so this is the displacement equal to 0 condition. This is the bending moment equal to 0 condition. Similarly, at x equal to L, we have displacement 0 and bending moment 0. So, let us consider this kind of a uniform simply supported Euler-Bernoulli beam. So, as we have discussed before, we search for a solution of this type, which is separated in space and time, complex solution. And if you substitute this in the equation of motion, the differential equation, then upon some simplifications this must be 0, where this prime denotes the derivative with respect to x. So, this is the differential equation. Along with this, corresponding to these boundary conditions, we will have so, we have a differential equation, ordinary differential equation in fourth order in W, which is the space function, and we have these 4 boundary conditions which defines what is known as the eigenvalue problem. Abbreviated as EVP. So, this is the eigenvalue problem that we now have to solve. Now, to solve this, we consider a solution of this form. So, let this be a solution of this differential equation. So, if you substitute this in the differential equation of the eigenvalue problem, and that implies. So, I have substituted this in this differential equation and made some simplifications to obtain this, which implies that this beta tilde square, so which is an unknown constant. So, that is related to the circular eigenfrequency. Now, so we have, so this can have 2 signs plus or minus, and therefore, this beta tilde will have 4 solutions, which we will represent as plus minus beta and plus minus I beta, where beta is so beta is 4th root of this quantity, and this beta tilde has these 4 solutions. Now, corresponding to these 4 solutions, therefore, the general solution of this function w x can be written as So, in terms of this exponential function, we can write the general solution. So, where these a 1, a 2, a 3, a 4 are arbitrary constants, possibly complex. Now, you can also write this So, by combining terms, you can also write it like in terms of hyperbolic and trigonometric functions. So, here again b 1, b 2, b 3, b 4 are now real constants. Now, we have to determine, or we have to I mean this solution, this general solution must satisfy these boundary conditions. So, if you put this let us say in the first boundary condition, so you will get if you use the second boundary condition, then this will get differentiated 2 times. So, this will give this will also get, all these terms will get differentiated 2 times. So, they will be cos beta square cos hyperbolic beta square sin hyperbolic minus beta square cos beta minus beta square sin beta. So, if you put x as 0, so these are the two conditions in terms of b 1 and b 3, and if you you can easily infer from here that so b 1 and b 3 must vanish for the boundary for we are considering boundary conditions of a simply supported Euler-Bernoulli beam. So, so b 1 and b 3 they vanish. Now, using the other two conditions, so these two conditions are so this will so these are the two equations that remain. And if we want to have non-trivial solutions of b 2, b 4, so if we want to have non-trivial solutions of b 2 and b 4, So, this I can write So, this is what we have. So, if we want to have non trivial solutions of B 2 and B 4, then the determinant of this matrix must vanish, and that will give us the condition. So, determinant of this is so it is minus 2 times. So, that must be 0. This is the so vanishing of this determinant for non trivial solutions of B 2 B 4, this vector leads us to this determinant equal to 0, and this is the characteristic equation for the simply supported Euler-Bernoulli beam. Now, this is not so this sign hyperbolic is 0 only at beta equal to 0, which will give us the trivial solution. So, now this, so for non-zero values of beta, because if beta is 0, then you see the frequency has to be 0. So, for this to be 0, we must have sin beta L must be 0. And that implies now this beta L, sin of beta L equal to 0, that can happen at infinitely many values of beta, which can be indexed. So, these are the values of beta n for which all these boundary conditions will be satisfied. Now, you see beta n is given, beta is given by this expression which has this omega. Therefore, using these two, so beta square is and that must be as we have obtained. So, this is indexed. So, omega n must also now get indexed. So, we have now the circular natural frequencies of a simply supported Euler-Bernoulli beam. Now, so this is for the Euler-Bernoulli. Now, if you look at the differential equation of the Rayleigh beam model, then the differential equation of the Rayleigh beam model reads so this is the differential equation of a uniform Rayleigh beam. So, this is the rotor inertia term, and if you follow the step similar to what we have just now done, then you will get the circular natural frequencies of the Rayleigh beam as so this is for the Rayleigh beam. So, we have this additional factor in the Rayleigh beam model, in the circular natural frequencies of a Rayleigh beam. So, now let us analyze this. Now, if you define, so we have this factor in the denominator, the square of this factor. Now, what is this factor? So, this is the length of the beam. The second moment of the area about the neutral axis I over the area of cross section of the beam. Now, this I over A is the radius of gyration square. So, under root of that is the radius of gyration. Now, length over the radius of gyration can be defined as the slenderness ratio. So, this length over the radius of gyration is the definition of slenderness ratio. So, it indicates how slender the beam is. So, if slenderness ratio is very high, which means the beam is actually very slender. So, the length is much larger than its cross sectional the dimensions of its cross sectional area. Now, this appears in the square of this appears in the denominator of this term. So, you see if the beam is very slender, which means slenderness ratio is very high, then so this term I can write as now, if the slenderness ratio is very high, then for lower modes this term is negligible, say n equal to 1, 2, and if the slenderness ratio is for example 10, suppose the slenderness ratio is 10. In that case, this factor is much smaller than 1. In that case, this ratio is almost 1. So, which means for very slender beams, the circular natural frequencies of the Rayleigh beam model should match with the Euler-Bernoulli beam, but then this term brings in the difference for higher modes. So, for higher modes the frequencies are going to differ. So, as we go to higher and higher modes, the frequencies, the circular natural frequencies are going to be different. So, let us look at a comparison of this circular natural frequencies of the Euler-Bernoulli and Rayleigh beam models. So, as you can see, at lower modes they are very close, but as you go to higher and higher modes the difference is appreciable. Now, let us understand why this additional term that comes in our circular natural frequency, I mean, see, the source of this term is obviously the rotary inertia term. So, that we can very easily see if we look at the differential equation of the Rayleigh beam, then we can very easily see that the source of this term is the rotary inertia term. Now, so which means the rotary inertia term is effective for higher modes. Now, to understand this, let us see what happens in the higher modes after we look at the eigen functions. Now, if you look at the eigen functions, if you do the analysis for the Euler-Bernoulli or Rayleigh beams, then so the eigen functions are obtained. So, we have these expressions of beta n, we will put in here and solve for B 2 B 4, then you will find that B 2 must vanish. So, only B 4 can exist. So, therefore, the eigen functions will all be the sine functions. So, these are the eigen functions, and these eigen functions are same for the string. So, let us look at these eigen functions. So, we have simply supported Euler-Bernoulli or Rayleigh beam. So, this the second So, this is the eigenfunction of the third mode. So, the mode shape is defined by these eigenfunctions. So, you have two nodes here, one node here and no node in the first mode. So, this is same as that of the string. Now, let us see what happens as we go to higher modes. So, if you calculate the curvature, then the curvature is increasing. As you go to higher and higher modes, the curvature is increasing, and this rotor inertia term. So, more is the curvature, more is the rotation of this element. So, as you go to higher and higher modes, this term it brings in this effect of increased effect of this term because of higher curvature and of course, because of higher frequency. So, as you go to higher modes, this term becomes substantial, and that then starts affecting the eigenfrequencies, which is not there for the lower modes. Now, you see if n is very high, suppose n tends to infinity, then you can easily see that this the frequencies become proportional to n. So, if n becomes much larger than 1, then this becomes proportional to n. So, this term becomes much greater than 1. So, we can drop this 1. So, square root of this will be n. So, here there is an n square. So, the Rayleigh beam circular natural frequencies will become proportional to n as you go to higher and higher modes. Whereas, for the Euler-Bernoulli beam it increases as n square, as you can see here. Now, let us discuss a uniform cantilever beam. This is another kind of boundary condition which is quite common. Now, in this case the boundary conditions are given by so on the built in end we have displacement 0 and the slope also 0. So, both of them are geometric boundary conditions on this end. On this end we have the bending moment and the shear force as 0. So, that gives us now the So, the equation of motion, it remains the same. So, we are considering an Euler-Bernoulli beam with these boundary conditions. Once again we search for separable solutions, and we consider so we have a space part and a time part. So, when we substitute, so the differential equation of the eigenvalue problem remains the same. Now, in this case of the so that it was the differential equation of the eigenvalue problem, along with the boundary conditions which we have now. So, that is the eigenvalue problem for the cantilever beam. So, the general solution is like this, and when we use these boundary conditions, we obtain the following 4 conditions. So, these conditions can be simplified and written in this form. So, for non-trivial solutions of B 1, B 2, B 3, B 4, the determinant of this matrix must vanish, and this leads us to, so if you calculate the determinant of this matrix, and this is the characteristic equation for the cantilever beam. Now, these are all transcendental equations. So, we have to solve them numerically. Now, if you plot these functions after some rearrangement, if you plot these functions, then we can have a graphical approximation for the solutions as shown in this picture. So, what we have done is we have written this cos beta L. So, this is the characteristic equation. We have written this as cos beta L is equal to minus 1 over cos hyperbolic beta L. So, and we have plotted this cos beta L. So, cos z, this is cos z, and minus 1 over cos hyperbolic z. So, there are two these two functions have been plotted, and the intersection of these two functions are marked by these unfilled circles. So, these are going to give us the circular natural frequencies for our cantilever beam. So, let us see what we have done. So, essentially we have plotted these two functions, and wherever they match, that gives us a solution of z, which is the solution of beta L. Now, let us look at this figure once again. Now, you can see that for higher, so each of them, as I indicated, they will tell us the circular natural frequency. So, for the higher modes, so higher frequencies, you see this 1 over cos hyperbolic z, it falls off very fast to almost 0. So, these points can be written as zeros of this function cos z is equal to 0. So, for higher modes, you can reduce this characteristic equation to this simplified characteristic equation cosine beta L equal to 0, which will, so this is, therefore, I can write this beta so beta L as approximately this. Now, what I will do is, in order to get to this, I will add, here beta gets indexed with n. So, this is some error. So, this beta into L will deviate from the zeros of cos beta L equal to 0, by these numbers E n. Now, this so when I have added this E n, this small error, then I can claim that this is a solution of this, and for E n, let us say E 1 is, if you calculate the first solution of this characteristic equation, then it will deviate from this value by this amount. If you calculate for the second mode, so beta 2 L, then it deviates from this value. If you calculate for the third mode, then it deviates from this value by this amount. So, as you can see, this is rapidly falling, this E n, the correction is rapidly diminishing. So, for higher modes, it suffices to use 2 n minus 1 over 2 times pi as beta n into L. Now, if you so then beta n square is therefore and as you know, this beta we have looked at this. So, beta n square is nothing but rho a over E I times omega, square root of that times omega n. So, this implies so, this is the expression of the circular natural frequency of a cantilever beam. Now, corresponding to these circular natural frequencies, one can calculate the eigen functions from the general solution that we discussed. So, these are obtained as now, let me just indicate how this has been obtained. So, this was what we had. Now, the first condition that we have from here is that so that implies B 3 is minus B 1. Similarly, from the second condition, Now, we have used this third condition. So, therefore, so with these two conditions we can write so that is proportional to this, and we have used the boundary conditions, and to from there, as you can see, we have solved this we have obtained this eigen function. So, so this term appears here. So, we have considered beta b 2 as 1, and at x equal to L we have used the boundary condition to obtain this factor b 1. So, this is the eigen, these are the eigen functions, again these are indexed. So, let us once look at these eigen functions. So, this is the first mode, characterized by this eigen function. This is the second mode, this is the third mode. So, you can see in the third mode there are two nodes, in the second mode there is only one node and no nodes in the first mode, and the slope here is 0, the displacement and slope as we expect. So, we have discussed the eigen the modal analysis of beams, which is essentially again solving an eigenvalue problem. So, we have looked at these two examples of a simply supported Euler-Bernoulli beam, and we have also looked at a simply supported Rayleigh beam, and we have understood the role of this rotary inertia on the effect of rotary inertia on the circular natural frequencies of the Rayleigh beam, and finally, we have looked at this Euler-Bernoulli cantilever beam. So, with that I conclude this lecture.